So it's my pleasure to welcome the first speaker of the Colloquium series for this semester. So it's Lionel Levine from Cornell Math Department. So Lionel's PhD is from Berkeley. And then after his PhD in 2007, he was at MIT for 3 years, and then joined Cornell in 2011.
That's right.
And so today he's going to talk about something that looks really interesting, Abelian networks.
Okay, thank you, Peter. Happy to be here. You can judge whether or not this is truly an applied math topic, but well, all math is eventually math waiting to be applied, and I think this math could be applied sooner rather than later. I'm going to try to give a pretty broad overview of the area of Abelian networks, and I'll touch on joint work with a number of people. Some themes for this talk. One is pattern formation from local rules. So Abelian networks are systems that have some very simple underlying dynamics, but produce some very complicated large-scale patterns, and we're interested in how that happens. Local to global principles. Often, if you can verify a property of each processor in an Abelian network, you can then show that the entire network has that property as well. And I'll show you several examples of that kind of phenomenon. Halting problem. How can you tell whether one of these networks is ever going to halt? And if I have time, I'll tell you about an algebraic invariant you can associate to an Abelian network called its critical group, which is a finite Abelian group that governs the long-term behavior of the network. So I thought I would start with a concrete example of an Abelian network before giving you the abstract definition. And I'm afraid I have too many slides, but I don't know which ones to delete, so I've set a alarm clock. When this rings, we move on to part 2, no matter where we are in part 1. So part 1 is on this particular example, the Abelian sandfile model. It's the oldest and most widely studied example of an Abelian network, and let me give you one concrete situation. I work in the square grid graph Z2, and I start with a pile of n chips at the origin. And I have a rule that a site is unstable if it has 4 or more chips. An unstable site can topple by sending one chip to each of its 4 nearest neighbors. So 1 chip north, 1 chip south, 1 chip east, 1 chip west. Okay, and by toppling an unstable site, even if its neighbors were stable, they each gained a chip during the toppling, so they may become unstable. So I might get a cascade of topplings. Okay. Suppose I continue toppling until there are no more unstable sites. This kind of idea goes back in the physics literature to a famous paper of Bach, Tang, and Wiesenfeld in 1987. And their original motivation is something that I won't talk about today. It goes under the name self-organized criticality. More recently, this kind of system has been studied from a pattern formation perspective, and that's more what we'll talk about in this talk. Also in the math literature, it's known as chip firing, and was studied by a lot of authors in combinatorics. Okay, let me give you an example to make sure we understand the rules. So suppose n was 16, there's 16 chips at the origin. 16 is bigger than 4, so we can topple, sending one to each neighbor. 12 is still bigger than 4, so we can topple again, and again, and again. Okay, and now the neighbors of the origin have become unstable, and I now have a choice of, I have several unstable sites, and I could topple them in several different orders. Suppose we topple this left neighbor first, and then the north neighbor, east neighbor, south neighbor. Now the origin again is unstable, and topple it. And now note that everything has strictly less than 4, so this is a stable configuration. Can't do any more topplings. And I ask you to note that in this example, my choice of ordering, the north one first, or the west one first, and the north one, and so on, didn't affect this final outcome. Well, that's true in much greater generality. It doesn't matter that we chose this initial configuration. It doesn't matter that we were working on the square grid. We could have worked on another graph. The final stable configuration won't depend on the choice of which sites to topple in what order. And something formally stronger is true. If you pick a particular site and you want to know how many times does it topple, that number doesn't depend on the order in which you topple. Okay, here's an example of what I mean by pattern formation. So this is a sand file of 1,000,000 chips in the square grid, all started at the origin, and each pixel in the picture corresponds to a site in the square grid, and it's colored according to the final stable configuration, how many chips remain there. So there are 4 pixel colors in this picture. For example, this blue color means that there are 3 chips at every site in this blue region. Well, a kind of general experiment we could do in the square grid or in higher dimensions, so we can work in ZD or an arbitrary dimension Z. We can start with some background chips, say fewer than 2D minus 1 per site. 2D is the threshold you need to topple in D dimensions because you have 2D neighbors. And then place n more chips at the origin and look at the set of sites that topple. So we're interested in what can we say about this set? Is it finite or infinite? If it's finite, what's its diameter? What's its shape? Here's the picture we saw 2 slides ago. This was no background chips, just n at the origin. Here's constant background 1 and constant background 2. You can see the kind of geometry of the final configuration really depends a lot on this background. Well, h equals 3 is also stable. Why didn't I include it on the previous slide? Okay, Steve says maybe it's not abelian. It's a good guess. It is still abelian. The abelian won't depend on the particular background.
Because maybe the set is infinite.
Yeah. Okay, this set Sn is infinite in this case. And even worse than that, every site will topple infinitely many times. So consider what happens if I start with a background of 3s and just add 1 more chip at the origin. Well, origin is unstable, it topples, now its neighbors are unstable, now this whole diamond is unstable, and so on. So if you topple in parallel, after n topplings, you'll have this big diamond that's entirely unstable, and every site will topple infinitely often. Okay, so this suggests we can classify backgrounds based on how stable they are. So on the one hand, we have robust backgrounds. So that's a background sigma such that no matter how many chips you add at the origin, you can stabilize it with only finitely many topplings. In that case, this set Sn will be finite. At the other extreme, we have this example we just saw where there's some n such that if you add just that many chips, every site will topple infinitely often. We call those explosive backgrounds. And there's one middle ground possibility, which is that for all n, you could stabilize sigma plus n chips at the origin, but it may require infinitely many topplings to stabilize it. What differentiates this from the explosive case is that each site will topple only finitely often, but infinitely many sites will topple. Okay, so I give you sigma. We want to know how can we classify it among these three categories. And in the robust case, we can ask further questions like, well, how many topplings does it take, and what is the set of sites to topple? So I'll tell you a little bit about what we can say about questions of that form. Let me first just show you a demo of one of these things in action. So this is for the background of two chips at every site, and I've added, I think, 5,000 chips at the origin, and it's in the process of stabilizing.
Having flashbacks. Wow.
Okay, so now we're stable. So what you saw was the parallel update, where each frame was, we scan the whole grid, identify all the unstable sites, topple them in parallel, and that made the evolution pleasingly symmetric, but we could have toppled in some other order and we would have arrived at this same final state. Okay. Here's something that took a little work to prove, that if your background is at most 2D minus 2 in D dimensions, the ZD, then you're in this robust phase where you only topple finitely often. And in fact, it only spreads as far as you think it should spread. Namely, it has diameter, the set of sites to topple has diameter order n to the 1 over d, so it has volume order n. So remember, 2D minus 1 is the biggest stable background. 2D is already unstable. You need 2D chips to topple. So, so this background, 2D minus 1, explodes. You could ask, well, what about in between 2D minus 2, 2D minus 1? Maybe you start most sites with 2D minus 2 chips, but a few sites start with 2D minus 1. And it turns out that's also enough to explode. So in particular, if you start with 2D minus 2 and then randomly drop additional chips, so each site independently with probability epsilon gets an additional chip, that's explosive. So in other words, if you then add n chips at the origin for a large enough n, every site will topple infinitely often. And you could ask, well, so is it important that these chips were randomly placed? The answer is no. You could also place them deterministically. For example, you could place them on a lattice in ZD, as long as your lattice intersects every coordinate hyperplane. So you might ask, I'll give you just a few clues about how we prove something like this. So it seems like a lot of work to prove an explosion, because you know, from the definition, you have to show every site tupples infinitely many times. That's a high bar to meet. Fortunately, there's a nice reduction that shows it's enough to check that every site tupples at least once. So this is a very quick argument, so let me show it. So suppose for contradiction that every site toppled at least once, but it wasn't the case that every site toppled infinitely often. Well, in that case, there's some site that finishes toppling, and we could consider the first one to finish toppling, call it x. Because every site topples at least once, each neighbor of x is going to topple at least one additional time, which means x receives 2D, at least 2D additional chips, which means X has to topple again, and that contradicts the fact that X finished toppling. So, okay, so this is a useful observation. Okay, let me show you what these things look like when they're actually exploding, and then I'll give you another clue to the proof. Let's see. So, okay, so what you're seeing is this light blue color is 2 chips, and these occasional dark blue pixels, which may or may not be visible, are 3 chips. So we've started with mostly 2s, occasional 3s, and now we're dropping chips one at a time here at the origin. And you can see not very much is happening. Looks pretty tame. Okay, until a certain point. So at this point, we've stopped adding additional chips at the origin, and we're just performing topplings.
This goes on to infinity?
Yes, so this laptop is a new model which actually has infinite memory, which means this will never stop. So yeah, actually, it's funny. I showed this in a seminar at MIT, and I left it running in the background while I went through the rest of my slides, and then went back to this, and it had stopped. So it simulates, some extra amount in memory that you're not seeing on the screen, but because it only simulates a finite window, it will actually eventually stop.
You have a finite number of chips, right?
Well, in the simulation, yes, but in reality, you have an infinite number, or in the math, you have an infinite number because the background configuration has 2 chips at every site, plus 3 at these rare sites.
So you've got a finite number above the background.
Above the background, you have a finite number. That's right.
Do you have any results about that transient time that we just observed?
Yeah. So the time when it suddenly went, from this little thing to filling up the whole square. So what that is basically, if you were to grow this send file on a background of only 2s without those additional 3s, it will be square shaped, and it will have diameter of order square root of n, where n is the number of chips you added. And then you have to wait long enough so that you have an extra site. So you have these extra chips in the background. If you wait long enough until this square is big enough so that you have an extra thing on each edge of the square, after that point you don't need to add any more chips, and you'll keep toppling. Every site will topple infinitely often.
Question about that?
Yeah.
Does that mean that you still need the additional lattice points beyond the first time that happens?
Yeah, you need them.
Okay.
So these 4 by themselves aren't enough. They're enough to make this square expand 1 larger. Okay, but then you need, to make it keep expanding, you need these extra sites, on the next layer, and so on. Okay, so from what we've seen, it seems like 2D minus 2 is the critical value. So below it, everything is robust, and above it, if you add just a few more arbitrarily small density of extra chips, you're explosive. But there's a surprise wrinkle to this story, which is that you can add extra chips. As long as you add them carefully in the right places, you can actually get as close as you like to the maximum density, 2D minus 1. So in particular, what you can do is add an extra chip at every site in this set lambda m, which is the set of all points in ZD, none of whose coordinates are divisible by m. So what you're doing is you're leaving occasional hyperplanes free of extra chips, but everything else, you add an extra chip. And it turns out this background is robust, so you can add as many chips n as you like at the origin. You will only get finitely many topplings, and the diameter of the set of sites that topple still has this nice order n to the 1 over d. So I like to think of this as sort of controlled burns in, or thinning of forests. You know, if you want to prevent a forest fire, well, you clearly want to reduce the density of trees in your forest, but it matters how you do it. So if you make occasional kind of bare strips that stop your forest fires from spreading, that's much more effective than if you just remove trees at random. Okay, here's a picture of one of these backgrounds close to density 3, which is the highest stable density, but it's still robust. Okay, just a clue to the proof of some of these results. And this should be a topic that's very familiar to applied mathematicians. The discrete Laplacian. So there's a very useful function here. Just the number of times each site topples. Call that u of x. And its discrete Laplacian is counting something nice. So discrete Laplacian is the sum of the values at the neighbors of x minus 2d times its value at x. Well, if you think about this sum in blue, every time y topples, y is a neighbor of x, it sends x one chip. So if I add u of y over all the neighbors y, I get the total number of chips received by x. Every time x topples, it emits 2d chips. And so this term in red is the total number of chips emitted. So discrete Laplacian of u is nothing but the net change in chips. And what that suggests is we could forget about the dynamics for a moment and just ask for what we call stabilizing functions. So you think of this function u1, it's an integer valued function on the lattice, and we'll call it stabilizing for a particular initial configuration tau, if when we take tau and add the discrete Laplacian of u1, we get a function that's pointwise at most 2d minus 1. So think of this u1 as it's a recipe for performing topplings without regard to whether those are legal in the dynamics or not. And we call u1 stabilizing if, as a result of performing the topplings, you got a final configuration that was stable. Now, a thing to notice about these stabilizing functions is they're closed under taking pointwise minimum. If u1 and u2 are stabilizing, then their pointwise minimum is also stabilizing, which suggests looking for the smallest stabilizing function. And so it turns out the smallest non-negative stabilizing function is exactly the odometer function. We call this the least action principle for SAM files, and it's extremely useful. So it frees you from having to worry about whether topplings are legal. And it's a good way to get upper bounds on this odometer function and therefore upper bounds on the set of sites that topple. So the way I interpret this least action principle in English is to say SAM files are lazy. Right? So it says, if you want to know how many times x is going to topple, that's u of x, what you should do is look over all possible toppling procedures, legal or not, and figure out what's the minimum number of times x can topple in order to produce a globally stable configuration. Actually, and if you run the dynamics, that's the number of times it will topple. So no site does more work than it has to do. So one way to think about this least action principle is as an integer program. So we're looking for the smallest integer valued function, on a lattice which is non-negative and has this upper bound on its Laplacian. Okay, and good reflex to have when you see an integer program is ask about its linear program relaxation. So suppose we drop the constraint that u is integer valued. So this also models a kind of particle dynamics, which we call the divisible sand file. So it's basically, it replaces the chips in the sand file with some continuous amount of mass at every lattice site. And the rule is that each site has a capacity of 2d minus 1. When it receives mass, it doesn't distribute it until it reaches its capacity. Once it fills up to capacity 2d minus 1, if it receives extra mass, it distributes it equally among the neighbors. So you can perform the same experiment that we did in the beginning. Start with mass n at the origin, and spread it out according to this divisible sand file rule, and see what happens. Well, the behavior is really different. So it turns out that so if you let n be the volume of the ball of radius r in Rd, so you start with enough mass to fill up a ball of radius r, then in fact the set of sites that topple, that's dr, is really close to that ball. It's contained in a ball of just constant larger radius and contains a ball of constant smaller radius. So this really is some visually striking representation of how much harder an integer program is than a linear program, right? So when you run the linear program, you get this beautiful spherical thing, which has very little error from the sphere. When you run this the corresponding integer program, well, maybe to a quick glance it looks roughly spherical. Right? In fact, still an open problem, but we strongly believe that this thing is not spherical. So if you look at this straight edge here, this really occupies a constant fraction of the boundary. It's not getting smaller as a proportion of the picture as the picture grows. And moreover, in the integer program, you get all this interesting pattern formation, which is completely missing in the linear program. Ah, that's our alarm. So we now move on to Abelian networks. Okay, in 1 minute we move on. So I have to mention a beautiful recent result of Wesley Pegden and Charles Smart, which explains why these two pictures look so similar. So this is a sand file of 100,000 particles in Z2 on background 2. This is 200,000 particles. Of course, if you do 200,000 particles, your sand will spread further out. So what I've done is rescale this picture by a factor of square root of 2 in each direction. So these pictures are in incomparable lattices, right? The lattice mesh here is a factor of root 2 smaller than the lattice mesh here. Nevertheless, from where you're sitting, they probably look close to identical. So Pegden and Smart have proved a form of existence of scaling limit of this picture, and we conjecture that this limit has a very interesting property. It's locally constant on an open dense set. So to explain why we think that, here's a zoomed in piece of one of these sand piles, and you can see that, well, there are different regions where different things are happening. So here you have this blue region where every vertex ended up with exactly 3 chips. Also here. Here you have some region where you're seeing a periodic pattern. Most vertices ended up with 3 chips, and then there's these occasional red ones which ended up with 0. And you can see this, here's a more complicated periodic pattern. When you take the weak star limit, as Pegden and Smart did, what you're seeing is not the individual pixel values, but the local averages of those values. So on each of these patches, you'll just see a constant. So we think that this whole picture breaks up into these patches. Okay, there are plenty of unsolved questions in the sandpile model, but we also want to see if we can adapt what we learned about sandpiles to more general systems. So here's a taxonomy of Abelian networks. The sandpile is one example. Rotor router is another example, which I'll define shortly. And here's various more general classes that lie in between. Okay, so what is an Abelian network? We're going to work on a directed graph G, could be finite or infinite. Z2 or ZD, like we considered in the first part of the talk, you can view it as a directed graph where each edge of the lattice, there's a directed edge in both directions. And at each vertex, we're going to have an automaton with some state space and some alphabet. And each of these automata will have one input feed and multiple output feeds. So each edge, it will have an output feed. Okay, so formally, what do we have? So for each vertex V and each edge coming out of V, we have a state transition map. It says that, well, given that I'm in a certain state and that I read a certain letter from my input feed, I transition to some new state. Okay, and I have a message passing function, which says, given that I'm in a certain state and I read a certain letter, I'm going to send 0, 1, or more messages along that edge. So think of this, you have this network of automata, and you could have the user send input to a particular processor or several processors. And then those processors might start sending messages to each other, and eventually you'd like to interpret the final states of the processors as the output. Now, in this generality, there's a huge problem with this setup, which is that order might matter a lot, right? So there might be many messages in the system, and depending on what order I process them, I could get a completely different output. Deepak Dar is a statistical physicist who works on sandpiles, and this whole project of Abelian networks of mine is pretty much inspired by this paragraph in one of his papers. He says, in many applications, especially in computer science, one considers such networks, automata networks like on the previous slide, where the speed of individual processors is unknown, and where the final state and outputs generated should not depend on these speeds. Then it is essential to construct the network so that the order at which messages arrive to the processors is immaterial. So Dar is asking, what kind of axioms do we need to guarantee the output won't depend on the order? Well, before we answer that, let's make a list of everything we could possibly hope for. To start with, we'd like the halting status not to depend on the order, right? It would be really bad if one particular execution halts, but some other execution never halts. Okay, if we give ourselves that, we'd like the final output not to depend on the order. And then we can get pickier. We're just making a wish list here, after all. So it wouldn't be too good if you could have one particularly fast execution, but if you choose some other execution order, it takes forever to finish. So let's ask the runtime not to depend on the order. Okay, and then you might get pickier and say, well, I don't want to overload one particular processor and make it do all the work. So let's say, let's ask that each processor does the same amount of work, regardless of the execution order. And I could even ask that each processor, processes the same number of letters of each type, regardless of the order. So it sounds like a lot to ask for, and you might think that we're just dreaming and we can't accomplish all this. So, are there any interesting examples of this? Okay, sandpile is one example, which I think it's fair to say is interesting. How is it an example? So I take the state space of my vertex to be integers from 0 through degree -1. I have just one letter in my alphabet. So think of letters as particles or chips. My transition function just increments by 1 mod the degree. And my message passing function says if I'm in state, so if I transition to state 0, I send one letter along each outgoing edge. Otherwise, I send nothing. Okay, so essentially what's happening is the internal state encodes the number of letters received mod d. Okay, and every time that number becomes 0 mod d, that means you have enough chips to do another toppling, and you send chips to each of your neighbors. Okay, so that's an example, but what is an abelian network in general? So it's a directed graph with an abelian processor at each vertex. So I have to tell you what an abelian processor is. Okay. So there are going to be 2 axioms, one for states and one for messages. So for any state in the state space and any 2 inputs, so these inputs are words in the input alphabet of that processor, such that this notation means the letters of W prime are a permutation of the letters of W. Okay, so suppose I take 2 inputs which are permutations of each other. The final state that this processor arrives at is the same for the 2 words. Okay, and the messages, it may not send the same word of messages along each edge, but you're going to require up to a permutation that sends the same word. Two comments about this definition. One, it's local, so to check something is an abelian network, you only have to check a property of each individual processor. And 2, a unary processor, by which we mean the input alphabet has size 1, is trivially abelian, right? If your input alphabet has size 1, then permuting the input has no effect, and so these axioms are just vacuous. This is going to be nice for us because what we'll show is that these purely local requirements actually imply a global abelian property for the whole network. There's a nice way of diagramming the states of a processor, which I'm going to skip for purposes of saving time. It turns out that these networks obey a least action principle, analogous to the one for SAN files. And I think I'll skip the exact statement of the least action principle. I'll just say that its consequences are that we get everything on our wish list. So if there's one, a complete word means an execution that halts. So if there's one execution that halts of length n, then all the legal executions have length at most n. So everything halts. If you have 2 legal executions that halt, then they have the same specific local runtime. In other words, you process the same number of letters of each type in the 2 executions. And any 2 executions produce the same output. So you can think of this as a local to global principle, right? It's saying if each processor is abelian, then the whole network is abelian. There turn out to be lots of principles of this form. So in later slides, I'll define some of these terms. If each processor is irreducible, the whole network is irreducible. If each processor is a periodic rotor, then the whole network is a periodic rotor, and so on. Let me start with rotors. So that's another concrete example of an abelian processor. So we define a rotor as a unary processor, so it accepts only one type of input. And it sends exactly one output message for each input message. Okay? for message, you should read letter on this slide. Someone told me message, they think of a whole string of letters. So sends exactly one output letter for each input letter. Okay? So if you input a single letter to a rotor network, well, that letter is just kind of, you can think of it as doing a walk in your graph, right? So wherever you input it, that processor is a rotor, so it's going to output one message to one, or one letter to one of its neighbors. And then that neighbor is also a rotor, so it'll output one letter, and so on. So there's just one letter at a time, and it's walking around your graph. Okay, well, like many natural concepts, this was reinvented several times in different fields. This walk is called ant walk in computer science, Eulerian walkers in physics, rotor walk in math. And it also gives you kind of mysterious instances of pattern formation. So this picture was made by taking a rotor network in the square grid Z2 and inputting a million messages to the origin. Just briefly show you my collaborator's website, Tobias Friedrich at the Max Planck Institute. So what we did is we were intrigued by this pattern, and we wanted to generate larger examples of it. So we found a way to sort of speed up these simulations, so you don't need to simulate every step of every rotor walk. And we able to generate really large instances of these outputs, and they're actually so large that you can't open them with a normal image viewer. So what Tobias has done is put this on a Google Maps interface, so you can scroll through it and zoom, and it's really a good way to waste a couple hours. There's really a lot of interesting pieces of this picture. If you zoom in on different areas, you see completely different sort of things. So I'll just show you what happens if you zoom in a little bit. So this last frame shows you finally the states of individual processors. Each square is a processor, and these black arrows are the rotors. So what the arrows indicate is the direction of last exit from each site. And these form an enormous spanning tree of this whole picture. So there's a lot to be explained about this picture, and very, very little of the structure of it is understood. Okay, so that was by way of defining what a rotor is. Okay, so I can explain now this third item. If each processor is a periodic rotor, then n is a periodic rotor. So what do I mean by that statement? So we'll say a rotor is periodic mod d if it has this state space z mod d and transition is incrementing by 1. So essentially a periodic mod d rotor is a processor which every time it receives an input, it outputs it along some edge, and that sequence of edges is periodic mod d. Now imagine you have a network of such things, and you designate some node as your input node and several nodes as your output nodes, and you view the whole thing as a big black box. So you drop a message into the input node, and it's going to perform one of these rotor walks and walk through this network, and eventually it'll end up at one of the output nodes. And then you can repeat the experiment, and when you repeat it, you may end up at a different output node because the internal states of the rotors inside have changed. So you can look at the sequence of which output node you end up at. And it's easy to show that sequence is eventually periodic. What's somewhat surprising is it's actually periodic. So it doesn't have any initial transient portion. So that's the content of of this statement. And there are refinements of it. So if each rotor is palindromic, meaning that its period reads the same forwards and backwards, then the entire network preserves this palindromic property. Okay. So if we're going to view this as a model of computation, we should think about the halting problem. So here's what I can tell you so far about the halting problem. You'll notice this isn't as specific as you'd like. So it's telling you, it's giving a condition for when a Abelian network halts on all inputs. So something I still don't know the answer to is whether there's a polynomial time way to decide whether a particular network halts on a particular input. And if anyone has ideas about that, please talk to me. Okay, if all it's, so the condition is all eigenvalues of a certain matrix have to have absolute value less than 1. And here's the matrix. Okay. The index set of the matrix is the total alphabet, disjoint union of the alphabets of all the processors. And the entry, the AB entry of the matrix, is on average how many A's are produced by sending an input of n B's to the relevant processor. Now to define this, you need to have some initial state for that processor. And a nice fact is that this limit doesn't actually depend on the initial state. So that's a consequence of this word irreducible that I've included here. So I haven't told you what irreducible is, but I may or may not get to it. Yeah, so okay. So this is the start of the kind of algebraic portion of the talk, which will define irreducible and will tell you about the critical group. So we've got all these automata, and so there are lots of monoids sitting around. In particular, there are local monoids. So for every vertex, I can look at the maps on its state space that are induced by processing a letter at that vertex. So that gives you a submonoid of the monoid of all maps from the state space to itself. I guess I should say for non-experts, so a monoid is like a group, but it may not have inverses. That's all the group axioms except for inverses. So this map may not be invertible, but you could certainly compose any two maps. So that's the multiplication of the monoid. And because of our axioms for Abelian processors, this is actually a commutative monoid. And moreover, if the state space is finite, it's a finite commutative monoid. So there's a very nice fact from abstract algebra that doesn't usually get taught it somehow gets missed in both undergraduate and graduate abstract algebra courses. It's a nice elementary fact about finite commutative monoids, which is that they always contain inside them canonically a finite Abelian group. And one way to construct that group is to take the product of all idempotents, and idempotent is something that squares to itself, and take the ideal that's generated by that element. So you can show that's a finite Abelian group with identity element E. People sometimes ask me for an example of this construction, and the simplest example to work through is just a cyclic monoid. So you take the natural numbers, mod out by one relation that k equals n for some fixed k and n. And I won't go through this, but you could check in this example that the group is z mod n minus k z. Okay, so let me define the critical group. So you can view your whole network. Suppose you have a network that halts on all inputs. View it as just a single big Abelian processor whose state space is the Cartesian product of all your state spaces, and whose input alphabet is the disjoint union of all your alphabets. Then this big processor has a monoid, which we'll call the global monoid, and we define its critical group as in the previous slide. So it's the subset, it's the ideal in that monoid generated by this product of all idempotencies. Okay, now that's a very abstract definition. So concretely, it gives you something very interesting. So unlike most groups that you meet in nature, this group actually has a very non-trivial identity element. So this particular example, we took a big 521 by 521 grid as our graph, and we took the sandpile network on that graph, where edges that lead outside this big 521 by 521 box, they all go to a single sink vertex that just absorbs chips and doesn't emit anything. Okay. So what this picture represents, again, there are 4 colors in the picture representing 0, 1, 2, or 3 chips. So this is a configuration of chips such that if I add it to any other recurrent configuration and then stabilize, I'll get back to the recurrent configuration that I started with. Let me define irreducible for you. So if we have a monoid action, so M is a monoid acting on a set Q, we call it irreducible if there's no way to partition the state space into 2 subsets which are invariant under the action. And now I can define recurrent for you, which I already mentioned in regard to the identity element. So if you have a monoid action, which is irreducible, there's a whole bunch of equivalent conditions. So condition 1 says that, so it's a condition on a state Q. So condition 1 says that you can get to state Q from any other state by applying something in the monoid. For example, condition 4 says you're fixed by applying the identity element. So the way to think about recurrent states is that they are the states you will see after a long time if you keep adding a lot of input to your system. Some states you can never get back to if you add suitable input. Other states you can always get back to, and those are the recurrent states. It turns out that if you do a rotor network on a graph G with some vertex fixed as your sink that just absorbs chips, that the recurrent states are precisely the spanning trees of G that are oriented toward the sink. And a fact that got a lot of attention among combinatorialists in the last decade or so is that, curiously, the sandpile network on G has the same number of recurrent states. So the number of recurrent states of the sandpile network is equal to the number of spanning trees of the graph. And there are many bijections out there explaining, why these two sets have the same cardinality. But here's what I feel is the real kind of underlying structural explanation. Anytime you have a finite commutative monoid acting on a set, you get a corresponding group action. So here EM is this ideal, which is the Abelian group sitting inside your monoid, and EQ is the subset of recurrent states. And there's a very nice, so properties of this monoid action give you corresponding properties of the group action in a way that's maybe stronger than you would at first think. So if you have an irreducible monoid action, then your group action is transitive. So you can get from any state to any other state by applying a group element. And if your monoid action is faithful, then the group action is free, meaning there's a unique way to get from any element to any other element. This isn't hard to prove, although at first it seems it's one of these great results where you feel like you're getting something for free, because these conditions on the monoid action are pretty weak, and the conditions on the group action are quite strong. So in particular, if you have a both free and transitive group action, then there's a unique way of getting, so for any two states, there's a unique group element that will take you from one to the other. And that turns out to be exactly the situation in abelian networks. So for any finite abelian network that halts on all inputs, if the processes are all irreducible, in the sense that each local monoid action is irreducible, then the critical group, that's this global algebraic invariant, has an action on recurrent states, which is free and transitive. So in particular, the cardinalities of the group and the set of recurrent states are the same. Okay, this is my last slide. Okay, there are lots of questions in this area. I mentioned already the refinement of the halting problem for a particular input. We saw the least action principle for sand piles can be written as an integer program. So abelian networks can compute certain integer programs. What else can they compute? And maybe more interesting, what can't they compute? Or what does it take them a long time to compute? So it would be interesting to place these things in some computational hierarchy. And pattern formation. So we'd like to understand the patterns that these networks generate, and again, whether they have some limitations. So I imagine, analogously to how, in physics you might try to infer some properties of elementary particles from some macroscopic behavior. Maybe you can't measure the particles directly. You could take the same viewpoint to cellular automata and say, suppose I don't know what the update rule of my automaton is. All I can see is macroscopically what its behavior is. What could I then infer about the underlying rule? So in particular, are there some kinds of behavior that are just too complicated to be generated by an abelian underlying rule? So are there some inherently non-abelian patterns? Okay, thanks a lot.
So, questions?
Yeah, in the back.
Since you mentioned the halting problem for abelian networks,
Yeah.
the busy beaver function for abelian networks. Suppose that I found the total number of states and I found the length of the input sequence, and you want to design an abelian network that runs for as long as possible and yet still halts. Can you get super exponential running time, any upper bound to lower bound at all?
Yeah, so there will be an upper bound. The way that you show halting is from Dixon's lemma, which is the fact that in natural numbers to the power k, there are no infinite antichains. So that gives you some bounds. I mean, compared to busy beaver, they're very tame. I think they're just ordinary exponential. But the question is that exponential the truth, or is it actually something smaller? Yeah.
Have you studied this? So most of these examples, all of these examples run some form of lattice. Have you studied anything that's not regular in its degree distribution? Because some of the definitions need to be flux dimensions, and I'm just sort of curious if there's any interesting generalizations in that direction.
Yeah. So okay.
Could you repeat the question?
Yeah, the question was, have we looked at any graphs that aren't regular? So lattice has every vertex has the same degree. That's not really essential. So if your vertices have different degree, most things don't need to be modified. For example, in sand file, just each vertex has a different toppling threshold. Okay. And these results about same number of recurrent sandpiles as spanning trees, all that holds for an arbitrary graph. Yeah.
Before answering the questions, what else can you compute? You have in this slide you can solve certain
Yes.
any characterization of types of integer programs they can solve.
Yeah, so the ones that I know they can solve are where the matrix in the integer program is a Laplacian type matrix. So it's what I think they call a M matrix. So it's one of these generalizations of positive definite that doesn't require symmetric. So whether they can solve any other integer programs where the matrix is something else, I don't know.
Any other questions? Okay, let's thank Lionel again and the speakers.